Hello guys, I am Kumar. Previously, I worked at Amazon and Media.net as software engineer. And coming to our love for DSA, I have achieved All India rank 12 in Google Codegem 2021 and All India rank 4 in Meta Facebook Hacker Cup. Happy Diwali to all of you. And for this Diwali, I have something very special for you guys in this video also and in the offer also. So there were many students who wanted to improve their hard level DSA skills to crack all the top tech companies online assessments interviews, and they wanted to boost their ratings in competitive programming. They wanted to master system design. So we have a special offer on Diwali for them for the new batch starting. You guys can check the link in the description. Our batches will be different for the intermediates, beginners, and advanced, and there will be further bifurcations for the working professionals and the freshers and college students. We give the daily live training, 850-hour course, one-to-one mentoring, referrals of top 500 companies, and many more things in our program. Already more than 1,000 students have been successful. So you guys can get the offer. So now let's check out the problem. Okay, it's very important to check out the problem which we're going to solve today. So let's go there. So guys, let's discuss this problem in detail. The rating of this problem is, as you can see, 2478. So if the rating of some problem is 2478, it's very close, to 2500. It means if you solve this problem correctly in the contest, you can become 7 stars on Codechef. That's the level of this problem. And we are going to solve. That's why I call it as 7-star rated problem. It's based on trees. This problem will explain you that you just need basic observations. Just with basic observations, you can get such high level ratings. So let's deep dive into the problem. So guys, the name of the problem is make a tree. It's looking very complicated. Let me make it easy for you. So guys, the first observation for the problem is that you are given n nodes. You have to convert them into a tree in minimum number of operations. You can add multiple edges to your graph as you want in one operation. So let me show you how it's actually working out. Okay, so let's say the first thing is that you are given some nodes like this. You want to convert them to a tree like this. So how can you do that? Very easy, right? You can say that, sir, we have some operation, right? So sir, in one operation only I can solve it now. I will, in one operation, I will add the edge from 1 to 2. Then I will add the edge from 2 to 3. Then I will add the edge from 3 to 4. So in first operation only I add 1 to 2 edge, 2 to 3 edge, and 3 to 4 edge. Okay. Yeah, this problem assumes that you know trees and graphs already. So we have added edge from 1 to 2, 2 to 3, 3 to 4 in one operation, and problem solved, sir. In operation 1, I added these edges, sir. No, beta. There is one more special condition in our particular problem, okay? So guys, the condition makes the whole problem interesting, by the way. So guys, yeah, let me write here 4. The condition is that, guys, if you add edge from x to y, na, you can never use the node x and y again. That's it, guys. That's it. So if I add the edge from 1 to 2 in operation 1, if I add the edge from 1 to 2, na, I cannot use 1 and 2 again. So I cannot say that I am adding the edge 2 to 3. This is not allowed. Why? Because it is written. See, if in an operation you add some edge from x to y, then you cannot use x and y again. So x and y cannot be used again. X and y cannot be used again. So this becomes very interesting actually now. So x and y cannot be used again. Now what to do and how to deal with this particular situation? So you can say na, that, sir, I will do the things in alternate manner. Simple. I will do things in alternate. Okay, hello guys. So we can do the things in alternate order, right? We can do the things in alternate order. What is the meaning of alternate order? I will add the edge from 1 to 2. Then I will add the edge from 3 to 4. So this is valid. This is valid. Why? See, 1 to 2, nothing is common of 1 and 2 with 3 and 4. So I hope you understood the whole problem. The whole problem is that you are given such empty nodes like this, and you have to convert them to the given tree in minimum number of operations. Okay. Okay. So in first operation, yeah, I can select the edge from 1 to 2. So I selected the edge from 1 to 2. Can I select 2 to 3? No, I cannot select 2 to 3 because 2 is getting repeated again. So 2 to 3 I cannot select, but alternate I can select 3 to 4 because 3 and 4 are totally different from 1 and 2. So guys, in first operation, I added the edges 1 to 2 and 3 to 4. Wow, awesome. In second operation, what will I do, guys? Now I can use any edges I want because now the operation number is different. When I was at operation 1, I cannot use same nodes. Here also I cannot use same nodes. But again a new operation is starting, so I can start from scratch here. So in operation 2, I will add the edge from 2 to 3 because here nothing is there. This is empty, so I can add 2 to 3. Again, if I had to do some more thing, I could not have used 2 and 3 again. So guys, in two operations, I'm able to convert our initial nodes to this tree. So 2 is the answer. Okay, 2 is the answer. Now guys, before we move ahead, let's do a very big observation. What is the biggest observation? Well, my lovely students. The biggest observation is actually pretty simple. Is that if this is our tree, if our tree is linear like this, okay, so we want to create a tree like this from these nodes. Node 1, node 2, 3, 4, 5, 6, 7. I want to convert it to this tree. Linear means you can see it's just like an array. So if you want to do this, then the answer is always 2. You can always do this in two operations. How? You will use the alternate method. First, in a first operation, you will use the edge 1 comma 2. Then nothing should be common, right? If I use 1 2, I cannot use 1 and 2 again in the same operation 1. So I will use 3 4, then 5 6. So 1 2, 3 4, 5 6. That's it. Now comes the second operation. Now I again start new. So this is the tree I have till now, okay, after first operation. Now what can I do? Now I can select 2 and 3 because now this is a new operation. 2 and 3 selected, but I cannot use 2 or 3 again in operation number 2. No problem. I will now select 4 5 and then I will select 6 7. So that's it, right? In two operations, problem solved. So guys, this is the second biggest observation. Second biggest observation is this. Okay, so I hope if we recap the problem, you are given n nodes which are not connected to any other nodes. Convert them to the given tree. Tree is nothing but a graph with n nodes, n minus 1 edges. In one operation, you can add multiple edges to your graph. But if you add the edge x to y in operation I, then you can never use node x and y again in the operation I. Okay, so clear. Linear trees, which I showed you right now, can always be solved in two operations. And if there are only two nodes, then it can be solved in one operation. See guys, if I give you only two nodes, special kind of linear tree, you have to convert this to this. So just do one operation, right? Done. So linear trees and two nodes, we have solved it. Guys, the next observation is that if this is a general tree, not a linear tree, answer will at least be equal to the maximum degree of the tree. Like, what a big observation is this, and it really makes me happy. Answer will always be at least the maximum degree of the tree. Let me show you. What is the degree of this node? 1. 1. 1. 1. Degree means the number of edges attached to this. See. The degree of this node is 3 because there are 3 edges like this. Okay, so like that, one, only one edge from here for this node, 1 1 1. But the degree of this is 5 because there are 5 edges. You can see na, edge number 1, edge number 2, edge number 3. So if I make a tree like this, okay, this is node number 1, node 2, 3, 4, 5, 6. These are having degree as 1 1 1 1 only. But this guy has a degree of 5 because it has 5 edges attached to it. Okay, so it will take at least 5 operations: O1, O2, O3, O4, O5. Why? Because in operation 1, I let's take a random edge. Let's take 1 comma 2. Can I again take 1 comma 3 in this same operation? If I take the edge 1, if I see, I have nodes like this, right? Yeah, 1 2 3 4 5. In first operation, if I create the edge 1 comma 2, can I create the edge 1 comma 3 in the same operation? No, because 1 is getting repeated. Repetition is not allowed. So you can only create one edge in one operation. Okay, so 1 comma 2 only you can do in the first operation. 1 comma 3 you can do in the second operation. 1 comma 4 you can do in the third operation, and this is 1 comma 5, and this is 1 comma 6. So basically guys, we come to know from this example that if any random tree is given to us, na, answer will always be equal or more than the maximum degree of the tree. Answer can never be less than that, no matter what is your tree. You can make any tree. Okay, let's say I make this tree. This guy's degree is 3, degree 1, degree 2, degree 1, degree 1, 1, 2, 3, 4, 5, degree 5, degree 1, 1, 1, 1, 1. So you can see those degrees, right? You can see those degrees. But I will say that answer will always be greater than equal to 5. Why? Because 1, 2, 3, this node itself will take 5 operation. This node itself will take 5 operations to build. Okay, this part of the tree, this part of the tree itself will take 5 operations to build. So others were also going to take some operations. So answer should be greater than equal to 5, man. That's common sense. Because if a node has 5 edges like this, I can use only one edge at a time. I cannot use this and this at the same time because this node will get repeated in that operation. So I hope you understand that if a node is attached to 5 other nodes, na, like this, it will take 5 operations. Why? Because in operation 1 I will select 1 comma 2. I cannot select 1 comma 2 along with 1 comma 3 because 1 becomes common. So this is clear that the answer will always be greater than equal to maximum degree of the tree. But guys, there is a catch. Our answer should always be equal to the maximum degree of the tree, right? But if you are able to make your answer equal to maximum degree of the tree, it means you have found the minimum possibility. See, it is common sense. आपको ये पता है कि आपका आंसर हमेशा मैक्सिमम डी, मैक्स डी जो है ना, इसके जितना ही इससे बड़ा ही होगा. तो आप अपने आंसर को इसके बराबर कर लो तो वो आपके लिए मिनिमम हो जाएगा, मिनिमम ऑपरेशंस आ जाएंगे. सो द बिगेस्ट ऑब्जर्वेशन इज, आई एम सो हैप्पी टू टेल यू that see, we are able to solve 7-star rated problems here. So answer will always be greater than equal to max degree of the tree. If you are able to construct the tree in D operations only, then it's guaranteed that you can achieve the answer in minimum operations, as less than D is not possible. So guys, now the task is that, see, such a lovely task now we have. Let's say this is our tree, okay? We have this tree. What are the degrees? 4, 1, 1, 3, 1, 1, 3, 1, 2, 1, 1 to 1 mentoring. Jokes apart. Jokes apart. So, guys, how will you solve this problem now? It's actually pretty simple. Actually, pretty simple. How? So, the thing is that you know now the degree. What's the degree going on, right? Maximum degree is 4. So, guys, our task is to solve it in 4 operations only. Operation 1, Operation 2, Operation 3, Operation 4. If you're able to solve in 4, your answer is correct because answer should always be greater than equal to 4. But you are able to do in 4 only. So you have achieved minimum operations. 4 से कम में हो ही नहीं सकता क्योंकि maximum degree is 4, so it cannot be less than 4. How will you solve it in 4 operations? The algorithm is travel all the nodes whose degree is 4 and remove one edge from them. So guys, which are the nodes which have degree 4? Here in operation 1, I will only deal with the guys whose degree is 4. Okay. So this is the guy whose degree is 4. So what can I do? Now guys, let's try to destroy the tree. Okay. Guys, rather than creating the tree, we can do the reverse process also, right? See, I've written here. Given the tree, we now have to destroy the tree in the minimum operations. If you can destroy the tree in 4 operations, if you do the reverse order, then you can make the tree also in 4 operations. So how will you destroy the tree in 4 operations? Focus on the node with degree 4. Only one node is there with the degree 4. Destroy this edge. Destroy. Yes, sir, destroyed. So this edge was this one, right? I destroyed this edge. Okay, one edge destroyed. Let's give them names now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in O1 operation, I will destroy the edge from 1 to 2. Okay. Yes, sir. Good. After destroying it, what has happened? This guy's degree has become 0. And this guy's degree has become 3. Now, guys, see! The best thing is that all the nodes now have their degree as less than equal to 3. Because all the nodes have their degree less than equal to 3, you can again do the same thing on the operation number 2. Go through all the nodes whose degree is 3 and try to make sure that all of them become 2, and keep on doing this process till the end and your job is done. It's so easy. Let's take a rather simple example for you people. Let's do that. Is the biggest observation for this problem, and it comes in such a humanly manner, right? That you are given a tree whose maximum degree is d, right? In one operation, you convert it into a tree whose maximum degree is d minus 1. Means all node degree should be less than equal to d minus 1. Then in the second operation, you make sure that the maximum degree of the tree becomes d minus 2. Okay. So what I'm trying to do is that, let's say I have a tree whose degree is 4. After O1, what should happen? Its degree should become 3. After second operation, the degree of tree should become 2. Then after this operation, third operation, degree should become 1. And if the degree of the tree is 1, it means it is looking like this. Two nodes connected to one edge. Degree 1. You can solve it easily in one operation. So it is solved when you reach d equal to 1. Okay. So how, I hope you understood, guys, what is happening. That you are having different, you have to convert to different trees. Okay. In O1 operation, if this was degree d, after this operation, the degree of the tree should be d minus 1. Then the degree of the tree should be d minus 2. Then d minus 3. Like should it like this, it should keep on decreasing. So guys, what will be the algorithm? Algorithm is to do a BFS from the top root. Okay. Let's start doing BFS here. What is the maximum degree, guys? Degree, maximum degree is of this node, right? 1, 2, 3, 4, right? So guys, I have to convert this degree 4 to degree 3 in O1. How can I do this? Guys, in O1, I have to select an edge which will decrease the degree of this tree from 4 to 3. It means I need to delete one edge from the node 2 because node 2 is having degree 4. One edge, two edge, three edge, four edge. So let's randomly delete this edge, the parent. Okay. So edge 1 to 2, if I delete, the degree of the tree has become 3. How? Guys, after deletion, how does the tree look like? Tree is looking like this. This node is like this here. This node is like this here. This is like this, and this. So guys, now we have two trees. It's a forest. Okay, it's a forest. What are the degrees? 1, 2, 3, 1, 1, 3, 1, 1. See guys, all nodes are having their degree less than equal to 3. It means you in O1 you successfully may converted the degree maximum degree of tree from 4 to 3. Now your job is to convert the degree of the tree from 3 to 2 in second operation. How we do that? Focus on the nodes which are having degree as 3. So there are only two nodes which are having degree 3, right? This node and this node. So randomly let's delete one edge. Okay. So I delete this edge. This edge is nothing but 1 to 4. And nothing is common. Okay. 1 and 4 totally different. And here let's randomly delete 2 to 7 or, or 2 to 5. See, it's being followed. None of the nodes are common in O2 operation. Guys, after this, how will the tree look like? Now the tree will look like this. Sorry. This, this, this. Guys, this is the tree now. You have a forest of 3 trees. Everyone is having the, see, here you successfully converted the degree from 3 to 2. Now you have to convert the degree from 2 to 1. And then you have to convert the degree from 1 to 0. But guys, this is simple. These are nothing but linear trees. See, whatever you are getting in the end, na. This guy has a degree 1. This guy has a degree 1. This guy has a degree 2. This guy has a degree 1, degree 1, degree 2, degree 1. Array, these all are linear trees. How do they look like? They look like this. If you stretch them, they look like this. You guys know how to solve linear trees in 2 operation. I taught you this in the start only. Take alternate. This in the first operation, this edge in the first operation, this edge in the first operation, and then the leftover edges in the second operation. Because these are linear trees. Guys, even if you have a set of linear trees, still you can solve them in 2 operations. Okay. So guys, as soon as you reach d equal to 2, you can stop the algorithm. You now know what to do. If the degree of each node is less than equal to 2, you know what to do. So we have successfully solved this problem with the BFS algorithm. Okay, very simple it was, right? So always remember why this set of trees can be solved in 2 operations. I want to prove it to you. Let's say you reach this situation. The maximum degree of this forest is 2. Why? Well, 1, 2, 2, 2, 1. This degree 1, degree 1, degree 1, 2, 1. 1. Okay. So how can you solve it in just 2 operations? If you reach d equal to 2, you just can do 2 operations. Use the alternate method which I taught you. What will you do? Select this alternate edge. First operation, this alternate edge. Here there is nothing, to select this one. This alternate edge. Destroy these in the first operation. And no node is coming common when you destroy this. Now whatever is left, destroy this in second operation, second operation, second operation. So I hope the full algorithm is now clear. What will you do, guys? You are given a tree like this. Okay, let's assume you are given a tree like this. First, you will find all the nodes whose degree is maximum. Okay, find all the nodes whose degree is maximum degree d, and start assume that one is the root node of the tree, and start doing BFS. First you will travel this node, then all the nodes on the second level, then all the nodes on the third level. Whenever you find a node, whenever you find a node whose degree is d, what will you do? Randomly remove some edge. Randomly remove edge. Guys, why should you randomly remove a edge? See, let's say this is the node whose degree is d, which is maximum. I am trying for the nodes whose degree is phi. I should now remove one edge, right? I need to make its degree 4. So which one can I remove? I can remove this one, or this one, or this one, or this one, or its parent. Always first remove the parent edge, okay? So remove this. If parent edge is not available, then remove the child edge, okay? So guys, I hope the algorithm is totally clear to you. That, see, I will show you two cases. Let's say this is the node whose degree is phi. You want to convert all the 5 degree nodes to 4 degree nodes. So here, it's always optimal to select its parent edge. Divide this one. But what if this was only our root node and there are 5 children? Then you can select any random child node and delete that edge. And its degree will become from 5 to 4, and here also 5 to 4. Okay, that's it. But guys, I hope you will take care of the corner cases also, right? Let's say this is your first node. You are targeting nodes with the degree phi. You delete this edge, right? Okay. Now you travel all the nodes in the second level. You come to know that 2 also has degree phi. But don't delete anything at node 2 even if it has degree phi, because in the past already 1 to 2 has come, so one deletion has already happened. Its degree also became 4 and this also automatically became 4. So whenever in your BFS, if you are at a particular node, BFS means what? Very simple. It means that first this guy was traveled, then second this guy turn came, and third the children node's turn came. Okay, so if this node was, if this edge was deleted, so this degree was also reduced by 1 and this was also reduced by 1. So if the parent edge is already deleted, then don't do anything, ignore. But if the parent edge is not deleted, then try to delete the parent edge. And if parent edge does not exist, then try to delete a child. Like this, if you do the algorithm, I hope this super hard problem you got the lovely intuition for it. So what is the final solution for it? Let's go back to our chart. So guys, we will do a simple BFS from root node of the tree and only focus on the nodes having degree SD, and we'll make all of them d minus 1. So tree with maximum degree d, in one operation will convert them to the tree with maximum degree d minus 1. In second operation will convert them to the tree whose maximum degree is d minus 3 till you know na. As soon as we reach the degree d equal to 2, it means all the trees are now linear trees. You can solve them in 2 operations. Done by using the alternate method. But guys, you know you have to do your BFS d times. So time complexity is n into d. Time complexity is n into d. Because you will do BFS again and again d times. See, when you want to make degree 4 to 3, again you will travel the tree, takes n time. Then you want to make degree 3 to 2, again you will travel n times. So n into d. So n can be 1000, d can also be 1000. So 10 raised to 6, you can solve the problem. It's efficient. Now, guys, we have discussed the greedy algorithm, but many people will not teach you this. But how to prove that this greedy algorithm is correct? That's what the people are not able to do in the contest. Okay. So, uh, someone can say, now, why are you doing BFS? Why are you not randomly selecting the nodes whose degree is D and remove the edges and get your job done? So, guys, there is a reason. Why are we not doing randomly? This is the reason. Please observe. Guys, let's say these are our trees, okay? Okay. Uh, yeah. Hope you like this brilliant explanation. Guys, can you see in this tree what is happening? The maximum degree of tree is 4, right? So in one operation, you should be able to make it a tree whose degree is 3. So let's randomly do it, okay? Guys, let's randomly do it. Why are you doing BFS? Someone can say, na, why are you doing BFS, man? Do it randomly, na? Okay, okay, doing randomly for you. So randomly, I come to know that this node has degree 4, this node has degree 4, this node has degree 4, degree 4, degree 4. So if I was doing BFS, I would consider this as the root node and I would solve from here to here, right? Level wise order BFS you must be knowing, but let's not do let's do randomly. Let's first tackle this one, okay? So you can say, sir, I will delete this edge. So its degree will become 3. Here also you randomly delete this edge, parent edge, right? Parent edge, right? So yeah, you have successfully converted this also to 3, this also to 3, this also to 3. All is happening in O1 operation only. None of the edges are common. All are distinct. No node is you getting used again. But here you get trapped, guys. Its degree is what? Sir, the degree is 4. Can you remove this edge? No. Because this node has been used while deleting this edge. Can you remove this edge? No. Because this edge has been used while when you deleted this edge. So this node and this node x to y got used. You cannot use. Can you use this? No. Can you use this? No. It remains as degree 4 only. You failed. आपको सारे के सारे नोट्स जिनकी डिग्री 4 थी उनको 3 में कन्वर्ट करना था एक ही ऑपरेशन में. ये नहीं किया तो मिनिमम नहीं हो पाएगा. और आपने क्या किया? आपने रैंडमली इनको तो कर लिया बट ये डिक्रीज हो ही नहीं पा रहा है क्योंकि ये जो दूसरे नोट्स इधर है ना ये सब ऑलरेडी यूज्ड है तो ये कोई भी एज डिलीट ही नहीं कर सकते तुम इधर ये एक ऑपरेशन में O1 में. So guys, I now hope you understand that if you randomly do na, you will get into trouble. Okay? But you are with Kumar K, you are in our program, you will never get in trouble. You will lead a very happy life, successful life, prosperous. So let's find out how to be very happy. Okay, let's find it out. So guys, this is the theorem which tells that you should always start with the root node and then go like this. Okay, but why does this work? I will tell you why does this work. Okay, now if I do it in the reverse order, na, it will start working. Like if I start doing BFS and start removing the nodes, then it will work. Degree is 4, right? This is also 4. 4, 4, 4, 4. So what I will do, I will follow simple algorithm. This is 4 now. BFS I am doing. First I will travel this node, then all the nodes in the second level, then all the nodes in the third level. So I will randomly select this edge. Yes sir, delete it. Now this node, do I need to delete anything? No, it has already been deleted. I will not delete anything. The degree has become 3 here. Okay, it has 3 nodes. Okay, okay, okay. I cannot delete the parent because the parent node has already been used. So I will delete any one of the child node. Here also delete one of the child nodes. Here also delete one of the edges of the child nodes. And guys, problem has been solved. This became 3. This became 3. This became, this remains 3. 3. 3. All degree 4 converted to 3. Why did it work out, guys? Why did it work out? Did this work out because if you do BFS, each node always has a child. So if you have no option, you can always delete edge with child node. Samjhe? That's why this algorithm is working. For example, let's say this node is in consideration, okay? Its degree is D, okay? Let's assume this has been used, the parent has been used, this also has been used. In case these things are used, okay, in the worst case, obviously you will not do anything, right? Now let's assume that there is a situation, let's say nothing exists above, and this is the node with degree D. At least this node has some children. So you can select an edge with the child and you can delete it and it will surely become D minus 1. So when you do BFS from top to bottom, how does the BFS look like? BFS look like this. I know no one will ever explain you with such in-depthness. How will BFS look like? First you will travel this, then you will travel all the nodes here, then you will travel all the nodes here, then you will, if you do like this ना, क्या होता है कि ये नोड के भी बच्चे हैं, तो वर्स्ट केस में कुछ नहीं मिला तो बच्चे को तो डिलीट करके D माइनस 1 हो सकता है. वैसा सिचुएशन नहीं होगा जैसे मैंने आपको रैंडम में दिखाया था. रैंडम में क्या हो गया था? रैंडम में ये हो गया था कि आपने रैंडमली नीचे से किया था ना, तो ये वाला एज सिलेक्टेड है, ये दिस एज आल्सो सिलेक्टेड. नाउ D इक्वल टू 4 प्रोसेस ही नहीं हो पा रहा क्योंकि बच्चे अवेलेबल ही नहीं है. बट आप ऊपर से नीचे जाओगे तो नीचे हमेशा खाली बच्चे मिलेंगे आपको. इफ यू गो लाइक दिस, let's say you have traveled this much, but now these guys have not been selected, so the children are always available for getting selected. अब कोई बोल सकता है सर बट व्हाट अबाउट लीफ, ये लीफ का तो कोई भी बच्चा नहीं है सर. अरे तो लीफ का डिग्री डी हो भी नहीं सकता. वी आर ट्राइंग फॉर डी इक्वल टू 4, डी इक्वल टू 3, बिग डी. डी इक्वल टू 2, डी इक्वल टू 1 का तो हम सॉल्व ही नहीं करते. वी नो हाउ टू ऑलरेडी सॉल्व इट. डी इक्वल टू 2, डी इक्वल टू 1. So guys, this is a really brilliant problem. It deserves to be a 7-star rated problem. Okay, so I hope you guys enjoyed it. Happy Diwali.